Well, this is a Sunday afternoon, and I hope all of you are having a good weekend. The supplemental lecture is going to cover some basic aspects of smooth muscle physiology. And up to this point, you've learned about how it is that skeletal muscle works. And now we're going to delve into how it is that smooth muscle works. So the key learning objectives are, number one, to know the anatomy of arteries, capillaries, and veins. The second is to know how the contractile state of smooth muscle is regulated. In skeletal muscle, you learned that this is a very complicated process. And somewhat similarly, the process in smooth muscle is also complicated, but much different than that in skeletal muscle. And in talking about how the contractile state of smooth muscle is regulated, we need to be thinking about three different pathways or mechanisms. The first are the so-called myogenic factors. And you can see after that statement, I've added parenthetically stretch, mechanical stretch of the muscle fiber itself, the smooth muscle fiber. There also are neurogenic factors. And here we emphasize the role and the importance of sympathetic neurons. And the third way in which the contractile state of smooth muscle can be regulated is known as the involvement of chemogenic factors. Specifically here, we're talking about the role of nitric oxide. In talking to you about the structure of the myosin molecule, I mentioned to you that the structure of a myosin molecule is a hexameric structure. It's made up of two myosin heavy chains, two regulatory myosin light chains, and two essential myosin light chains. And in smooth muscle, it's the phosphorylation of the regulatory myosin light chain that plays a key role in determining whether the contractile process is on or off. And the factors that determine the phosphorylation state of the regulatory myosin light chain are myosin light chain kinase. The abbreviation for that is MLCK. And as all of you know, kinases phosphorylate their target molecule. So in this case, myosin light chain kinase is responsible for the phosphorylation of the regulatory myosin light chain. There also is the other side of this coin, so to speak, the involvement of myosin light chain phosphatase. And phosphatases are involved in removing phosphates. This leads to turning off the contractile apparatus in smooth muscle. And then also, you can see that the fourth learning objective is to know how smooth muscle can be pharmacologically manipulated to treat things like hypertension. So coming back to the first learning objective, I just want to briefly highlight some key aspects of the different types of blood vessels found in the cardiovascular system. So to your left, over here, you can see a representation for an artery that's shown down here at the bottom. And we're going to begin to refer to arteries as resistance vessels. Over to the right, you can see, the far right, you can see a representation of a vein. And we're going to refer to veins as capacitance vessels. And in between these two, we have the presence of capillaries. And it's here at the level of the capillaries that we have things like gas exchange, the movement of ions into and out of the circulatory system, the movement of metabolites into and out of the circulatory system. And remember that diffusion only occurs effectively at the capillary level. So if we come along and we take a look at the structure of an artery, there are three different levels of organization. there's the tunica intima, which is highlighted here. And the tunica intima makes up the walls of the lumen, and it's endothelial cells that make up the walls of the lumen. The lumen is the opening of the blood vessel. Moving outward from the tunica intima, we have the tunica media that's shown here. And the tunica media is where we find the smooth muscle cells and elastic fibers. And this is really where our story of smooth muscle comes into play as it relates to the cardiovascular system. Smooth muscle also plays a key role in regulating the diameters or the radius of bronchioles in the lungs, and of course also the gastric mobility of the gut. So smooth muscles play a really, really important role in our physiology. And then coming back to the structure of blood vessels, we have the tunica externa. And this is where we see collagen fibers. And then, of course, if you sit there and compare what you see in the left in terms of the structure of the artery with that is shown to the right, you'll notice that number one, the thickness of the tunica media is much less. That's highlighted right here by this the structure here, as opposed to over here in this light blue arrow. So in veins, the thickness of the tunica media is much less than it is in arteries and arterioles. And then also, not to be forgotten, is the fact that within the veins, as highlighted here, where we see the flow of blood moving upward, there's a presence of valves that ensure that blood only flows in one direction throughout the circulatory system. So this is just meant to give you an overview of where smooth muscle cells play a key role in regulating the diameters of arteries and veins. And from here now, what I want to do is I want to begin to address the second learning objective, which is how is it that the contractile state in smooth muscle is regulated? So to explain this, I'm going to just start off with a box. And this will represent a smooth muscle cell. And I'm going to show the presence of a myosin molecule. There's a globular head of the myosin molecule. And I'm going to show a different version of this. And what I want you to understand is that these are the same myosin molecule, just in different states. So over here, we're going to say that this is the off state versus over here is the on state. A different way of representing this is a detached or attached state. And we need to show the presence of our regulatory myosin light chain. And I'm just going to represent that as shown here in light blue. So I'll just come along and I'm just going to draw a blue arrow on over to here. And I'm going to put a label here that reads regulatory myosin light chain. And you have to understand, you need to know that it's the phosphorylation or the dephosphorylation of the regulatory myosin light chain that determines whether the myosin molecule is turned on or off. In the on state, it's going to be producing force or tension. In the off state, it will not be producing force or tension. So here I'm going to draw a red arrow showing the myosin molecule transitioning from an off to an on state. And this transition from the on to the off state is determined by the activity of the myosin light chain kinase. So here I'm going to put M, L, T, K. And that, by turning on myosin light chain kinase, we will phosphorylate the regulatory myosin light chain. How do we turn off, or how do we dephosphorylate the regulatory myosin light chain? And to do that, I'm just searching for a color here to use. Bear with me. To dephosphorylate the regulatory myosin light chain kinase, that involves the so-called myosin light chain phosphatase, MLCP. So ultimately, at the end of the day, what determines whether a myosin molecule in smooth muscle is turned on is the phosphorylation of the regulatory myosin light chain. And of course, if we dephosphorylate the regulatory myosin light chain, then we go from the on state, which you see to the right, to the off state, which I'm showing over to the left. And now the question is, how do we regulate these two molecules? So if we go back to the learning objectives, I mentioned that the way in which we control the contractile state of myosin in smooth muscle is through three different pathways. So-called myogenic pathway. Second pathway is the neurogenic factors, which involves the sympathetic neurons or sympathetic nervous system. And the third is through chemogenic factors. And that's what I'm going to begin to lay out for you now. So we're going to talk about these myogenic factors, neurogenic factors, and chemogenic factors. So here's our simple old drawing. And now we're going to come along, and I'm going to show the presence of an ion channel. And this is we'll say a stretch activated. So before I go any further, let me just write up here, myogenic factors, myogenic factor. This is number one. And really what we're talking about is the involvement of stretch, activated, calcium ion channels. And that's what I'm showing in green. Oops. So when a muscle cell is stretched, that causes these calcium ion channels to open up. And in so doing, calcium ions flow into the cell according to their electrochemical gradient. And one of the mechanisms that you've learned about is that within cells, there can be this calcium binding protein known as calmodulin. So calmodulin binds to calcium. And as you also know, we talked about turning a protein kinase on, so causing a protein kinase to go from an inactive to an active state. And so, in fact, what happens is when calcium binds to calmodulin, this then acts on a specific type of kinase. And in this case, it's myosin light chain kinase. And here in parentheses, I'm going to put a positive sign to indicate that when calcium is bound to calmodulin, it causes the myosin light chain kinase to turn on, which then leads to the phosphorylation of the regulatory myosin light chain, which will lead to an increase in force production. That's a pretty cool story, and it helps to provide more specificity to the general way in which calcium can exert some type of intracellular effect. And here now you know that in smooth muscle it plays a key role in terms of turning on myosin light chain kinase. Well, there's a second set of factors that can determine the on-off state of smooth muscle, and those are the neurogenic factors. So over here to the right, I'm going to put number 2, and I'm going to simply write neurogenic factors. And here we're really talking about the involvement primarily of the sympathetic nervous system. So let's add a little bit more to our scheme that we're developing. And here I'm going to show the presence of the sarcoplasmic reticulum. So I'm going to write the initials for sarcoplasmic reticulum, SR, inside this box. And located within the membranes, within the membrane of the sarcoplasmic reticulum, is a receptor-gated calcium ion channel. So here I'm going to write capital R, capital G, CA, I period, C period. You're going to read that as receptor-gated calcium ion channel. We know that the concentration of calcium inside the sarcoplasmic reticulum is very high. So there's a strong electrochemical gradient that favors the efflux of calcium out of the sarcoplasmic reticulum. And underneath the neurogenic factors, I'm going to write primarily involvement of sympathetic neurons. Here's a So here's our sympathetic neuron. And we're going to say that this is a, let me just write that here. And we'll say that in this case, the sympathetic neuron is releasing norepinephrine, and that norepinephrine is binding to a alpha-1 adrenergic receptor. And as you know, when norepinephrine binds to this alpha-1 adrenergic receptor, that then acts on phospholipase C. That was good. And when norepinephrine binds this alpha-1 adrenergic receptor, that turns on phospholipase C. Phospholipase C then converts PIP2 into IP3. IP3 then diffuses throughout the cell and binds to the receptor-gated calcium ion channel. And when that occurs, calcium ions then flow out of the sarcoplasmic reticulum and in so doing, they bind, those calcium ions bind to calmodulin. And through this set of events, we can turn on myosin light chain kinase, which will lead to the phosphorylation of the regulatory myosin light chain, causing the myosin molecule to go through its power stroke and develop force. That's pretty cool because that ties together a lot of the stuff that you've learned in studying the sympathetic and the parasympathetic branches of the autonomic nervous system. Well, instead of having a sympathetic neuron that's acting on the alpha-1 adrenergic receptor, we could instead have beta-2 adrenergic receptors. So here's another instance of the involvement of a sympathetic neuron. And in this case, you know that when norepinephrine binds to the beta adrenergic receptor, that acts on a stimulatory G protein. And ultimately, what that's going to do is that's going to lead to an increase in cyclic AMP levels. This increase in cyclic AMP levels, however, comes along and it will actually have a negative impact on myosin light chain kinase. So in this case, high levels of cyclic AMP actually inhibit the myosin light chain kinase. So here I'm going to simply draw an arrow, an orange arrow. Well, actually, I'll do the black arrow just to be consistent. So I'm going to put beneath this black arrow a negative sign to simply indicate that elevation in cyclic AMP actually turns off myosin light chain kinase, which would reduce the phosphorylation of the regulatory myosin light chain, which would reduce the force production of the smooth muscle cell. We can also have the involvement of sympathetic neurons acting on alpha 2 adrenergic receptors. And here you would say that the alpha 2 adrenergic receptor would act on an inhibitory G protein. So this would cause cyclic AMP levels to go down. This actually would have a beneficial effect for force production because it would remove the inhibition of cyclic AMP on myosin light chain kinase. So here we're going to draw an arrow, dashed arrow, coming back onto myosin light chain kinase. You can see everything thus far has been focused on myosin light chain kinase and regulating whether it's turned on or turned off. Here I'm going to put a positive sign because cyclic AMP is an inhibitor of myosin light chain kinase. So if we get rid of cyclic AMP, that then removes the inhibition from myosin light chain kinase. All right. Let's also show the additional involvement of these alpha-1 adrenergic receptors can also be acting through a different mechanism. So let me just show that here as well. So here's our sympathetic neuron. We've got norepinephrine. And here, norepinephrine is acting on alpha-1 adrenergic receptors. So we showed alpha-1 adrenergic receptors up above here, regulating the levels of IP3, but simultaneously, they're regulating the levels of a molecule known as Rho kinase, RHO kinase. And Rho kinase actually is acting on myosin light chain phosphatase. And here, this has a negative impact on myosin light chain phosphatase. So now here what you've got to do is you've got to combine two things. Is that we've got the alpha-1 adrenergic receptor, which I'm showing up at the top here. And this is turning on myosin light chain kinase. And at the same time, by acting through the alpha-1 adrenergic receptor and regulating Rho kinase, we're actually inhibiting, we're turning off myosin light chain phosphatase, which is exactly what we should be doing. So through the involvement of the release of calcium from the sarcoplasmic reticulum and binding to calmodulin, we're turning on myosin light chain kinase that favors the phosphorylation of the regulatory myosin light chain, and simultaneously we're inhibiting myosin light chain phosphatase, which would normally turn off the phosphorylation, or it would remove phosphates from the regulatory myosin light chain. So we're inhibiting that. So both of these culminate or contribute to force production. All right, we've got one other factor to add into this, and this is the so-called chemogenic factors. So this scheme that I'm laying out here, down here in the bottom left, we're going to put, that was a crummy looking 3, try that a little bit again. We're going to write chemogenic factors. And this one's quite important. So what we're going to do is I'm going to show down beneath here, we're going to show the presence of a blood vessel. So here's the lumen of a blood vessel. And around this blood vessel, we've got these endothelial cells. Where did my little black pen go? There we go. So I'm going to just put these little elliptical structures. And we'll come in and we're going to label these. So this is a blood vessel showing the lumen in red. And then we've got these so-called endothelial cells. And as blood flows through this blood vessel, so here I'm going to write flow of blood. There's red blood cells flowing along the surface of these endothelial cells. And this creates what's called a shear force. And the shear force causes these endothelial cells to produce a molecule known as nitric oxide, NO. Yeah, that was good. And the NO acts on these cells and causes them to produce cyclic GMP. And cyclic GMP comes along and it acts on myosin light chain phosphatase. And here it turns on myosin light chain phosphatase. And this causes the relaxation of smooth muscle and will cause the dilation of smooth muscle. So really a very cool process. Now, the last objective in this lecture is to describe for you how smooth muscle can be pharmacologically manipulated to treat hypertension. So there is a drug known as doxazosin. And doxazosin is a alpha-1 antagonist. So if you sit there and come back to our alpha-1 adrenergic system, sorry for that, hold on here. So our alpha-1 adrenergic system is going to turn on myosin light chain kinase. That's going to cause the smooth muscle cells to contract, and that will then cause the radius or the diameter of the blood vessel to decrease, which will cause an increase in resistance. So here I'm just going to write alpha-1 causes an increase in force, which leads to an increase, which leads to a decrease in the radius of the blood vessel, which leads to an increase in resistance. So let's place this in the context of blood pressure. So you've been exposed to Ohm's law. Ohm's law says that the flow rate is equal to delta T divided by R. Let's rearrange this equation to solve for pressure. So we would say that pressure is equal to the flow rate times resistance. So if the alpha-1 adrenergic system is turned on, the smooth muscle cells basically contract, decreasing the radius of the blood vessel. That leads to an increase in resistance. So according to this simple formula that I just mapped out here for you, the increase in resistance is going to lead to an increase in pressure. So we could come along and we can actually try to treat blood pressure using drugs like doxazosin, which is an alpha-1 antagonist. And there, what will happen is we come along and let's just put here doxazosin. I'm just going to write dox leads to a increase in the radius of the blood vessel because it causes relaxation of the smooth muscles, which will then lead to a decrease in resistance. And according to this equation, this version of Ohm's law, by decreasing the resistance, we will also decrease pressure. All right, so that's the supplemental lecture. There's a lot in here. The nice thing about this is that it fuses together, it provides a fusion of what you've learned previously with regards to the sympathetic nervous system and the various receptors associated with it. Also, this story involves the importance of stretch-activated ion channels and chemogenic factors like nitric oxide. So with that, I hope that this provides a good connection for you in terms of thinking about blood pressure and smooth muscle regulation. And I look forward to seeing you in class tomorrow night. Take care. Bye-bye.